So finish discussing superconductivity, and the lecture will be organized as follows. In the first half, we discussed with the blackboard some properties of superconductors, in particular tunnel density of states and thermodynamics, because this is important to demonstrate what's going on with thermodynamics if your excitation spectrum has a gap. And then in the second part of the lecture, I will turn off the recording and I will show you whole summary for superconductivity with slides, including slides for high temperature superconductors. So this is how we split our lecture in two parts. Okay, so what has been discussed on Monday that we solved the many-body problem, assuming that there is attraction between electrons in the vicinity of the thermal surface, and we discovered that the ground state of such system is unstable with respect to formation of the gap. So the gap, which is order parameter, appears at temperatures below Tc, and as a result, the spectrum of elementary excitations becomes gapful. So this is Kf, this is K, and this is epsilon K, and as we wrote, Ek is square root of psi K square plus delta square. So we said that the system is unstable with respect to formation of the Cooper pairs. We introduce the coherence length. Actually, we did it when discussed Ginzburg-Landau equations already. Let me write it epsilon K minus mu square plus delta square to understand what it means, and coherence length, which behaves as 1 over square root over tau. And we briefly discussed that this coherence length, which originates from the part of Ginzburg-Landau equation responsible for kinetic energy, is in principle associated with the typical size of the wave function. This is what I did by linearizing the Ginzburg-Landau equation. And again, maybe I should give a little correction. So what we did, there was the Ginzburg-Landau equation minus chi plus chi modulus square minus h square over 4m nabla minus 2ie over h bar square chi equal to 0. What I said that A is equal to 0. Just for discussion, we assume that there is no magnetic field, and we said that the uniform solution chi node is equal to 1 is everywhere, and we disturb it just at the origin. So chi is equal to chi node plus delta chi r. And by linearizing this equation for delta chi r, we obtain that delta chi r behaves in three-dimensional case. This is my only correction, as minus r over psi divided by r. In one-dimensional case, it will be just exponent, as we see, and the equation, which is 4m. So this is basically psi square, psi minus 2, psi square. Yeah, this is what we had. Okay, so solution in fact does depend on dimensionality, and you were right. So I apologize for this. So what we said then, that this psi square, which is h squared over 4m alpha tau, this is a coherence length. And this coherence length actually defines the typical size of your wave function, and we know that the order parameter is a gap, and at the same time it's attributed to the wave function. So psi, I would say, is a typical size of the Cooper pair. And of course, since this psi actually is a very large quantity, we can immediately say that different states Cooper pairs overlap Cooper pair is singlet overlap strongly, and we cannot discuss the Cooper pair as a bosonic quasi-particle because the size, typical size of this Cooper pair is much larger compared to the distance, mean distance between Cooper pairs. So this is why, and this was a reason why the solution of a Cooper problem demonstrated on the first lecture about superconductivity, assuming that Cooper pair can be considered as a small object and we can treat Cooper pairs as bound state, was incorrect. This was a reason, and instead, as I said, we do have spontaneous symmetry breaking, which results in formation of the Cooper pairs, and because of the existence of the Cooper pairs, the spectrum of elementary excitations, electrons and hole, requires the gaps. So let's see how this gap manifests itself in tunnel density of states, tunnel current, and thermodynamics. Good? Okay, so density of states, and omega is 2 times integral over dp over 2 pi cube. I consider standard conventional 3-dimensional superconductors. This is delta omega minus spectrum square root over p square over 2m minus mu square plus delta square. So let's compute this the same way as we did it for the normal methods. First of all, nothing depends on angles. So factor 2 comes from spin. So we have 2 4 pi solid angle divided by 8 pi cube. Then we introduce a new variable. So I will multiply by m and divide by m. So here we have p square root p square over 2m, and I can subtract mu here. This will be my new variable. Okay, and we have this delta function omega minus square root over p square over 2m minus mu square plus delta square. So if I introduce this variable and call it x, so the integral over p is from 0 to infinity. If we say that this is x, then p is equal to square root over 2m mu minus x, right? And this integral is integral from x p is equal to 0, this is minus mu, to infinity, square root over 2m mu plus x, because this is x, mu plus x, and delta function omega minus square root over x square plus delta square. So first of all, you remember, and we discussed it in details, that the density of states of free electron gas characterized by quadratic dispersion law behaves as a square root over energy. So this is new energy as a function of energy. And the first step what I will do, I will replace this factor. This is integral over dx. I will replace this factor by its value at the Fermi surface. Because what we are doing, we are discussing effects associated with EF plus delta and EF minus delta. And this is a tiny, tiny stripe in the vicinity of Fermi energy. So this goes out and gives me actually PF. And as a result, the factor, this one is MPF over pi square. This is the density of states of the non-interacting Fermi gas, and we have integral from minus mu to infinity dx delta function omega minus square root over x square plus delta square. The delta function is even function of its argument, and if I say that this is function minus fx, then using the rules of calculating integral with delta function, this is mpf over pi square, and I have 1 over modulus f prime at the point where fx is equal to 0. So I need to find node fx, need to find the derivative, and then I'll get the density of states. Okay, so fx is square root over x square plus delta square minus omega minus omega. So fx equal to 0 means x equal to plus minus square root over omega square minus delta square. And you see already that there is some problem for omega smaller than delta. So this x becomes complex, which means that this region of energy is not accessible. So f prime x is equal to x divided by square root over x square plus delta square. So then at the point x equal to x node, this is plus minus square root over omega square minus delta square divided by omega. So what we see here, that this is MPF over pi square omega divided by omega square minus delta square. So the density of states, I zoom in this area minus delta. Delta has 1 over square root singularity, so this is n omega. This is omega, and if we put all things together, we are discussing in a bit exaggerated way this. In fact, that because of the gap, we have no states in the stripe between minus delta and delta, and the density of states has 1 over square root singularity, the very same way as we discussed it with Landau levels, where the density of states, because of quantization of the energy associated with the degeneracy in directions x, y, results in the 1 over square root singularity of the density of states. Okay, what does it mean from the practical point of view? Let's consider experiment that we put two materials, 1 and 2, in tunnel contact and put a battery. So the current I is proportional to the integral over the energy. This will be, let me be more precise, density of states over energy, density of states over voltage minus energy. I don't put proportionality coefficient. So suppose that 1 and 2 are metals. So if 1 and 2 are metals, so let me write the density of states on the left hand side and the density of states on the right hand side. So these are carriers. We apply a small bias. So this is voltage applied to the system. And as soon as we apply bias, the current starts to flow. Therefore, what we have is so-called Ohm law. Current is proportional to the voltage. So if 1 and 2 are metals, 1, 2 metals. So consider then the situation when 1 is metal and 2 is superconductor with this 1 over square root density of states. Then what happens that we are in the gap. So this is metal, this is a superconductor. This is 2 delta. So we need to apply bias actually larger than the gap, and then the current flows. So the IV curve or dependence of the current function of voltage becomes highly nonlinear, and there is no current for the voltage is smaller than the gap. Okay? Let's now consider what happens. So this is 1 metal, 2 superconductor. As I mentioned, this was one of the key experiments which demonstrated existence of the gap. And in fact, the theory which we discussed during the last 3 lectures fully confirms and explains this experiment. So the last exercise is what happens if we have the tunnel contact between 2 superconductors. Let's say they are different, might be different superconductors. Here it's delta 2, delta 1 and delta 2, because it's more easy to plot that. But what then happen, I have a match this band with this band, therefore the current starts from delta 1 plus delta 2, and then it goes abruptly and it saturates. So this is situation 1, 1 is superconductor 1 and 2 is superconductor 2. Okay? Again, it's full agreement with experimental observation. Good. Let's now see how the gap manifests in thermodynamics. Let's compute specific heat and discuss the specific heat in 2 limits, namely the behavior of specific heat when the temperature is much lower compared to superconducting gap, and when temperature is approaching the critical temperature of superconducting transition. And actually, what I'm saying to you is generic for any fermionic and to some extent bosonic system characterized by the gap in the energy spectrum. Okay. Suppose we have a Fermi liquid. So specific heat CV is associated with delta E total over delta T. The total energy is sum over K epsilon K. So I will write d E total over delta nk. This is our excitation energy times delta nk over delta t. So we need to differentiate the Fermi distribution function. This is our epsilon k. Well, I should put factor of 2 because of summation of a spin, and I assume that there is no magnetic field at this very moment. So this is what I would call, I would write 2 sum over k epsilon k delta nk over delta temperature. With the very same approach as we discussed on Monday, d delta total over dnk, this is our square root. So in a superconductor, we write the same. CV is sum over k factor of 2, and we have this square root of xi square plus delta square times delta nk over delta temperature, where nk is the Fermi distribution function e to the power square root of xi square plus delta square divided by temperature plus 1. Important and subtle point here is that delta depends on temperature also here. But we differentiate with respect to temperature, only distribution function, because of this Fermi liquid arguments that this is a spectrum. Okay? So, then it's 2 sum over k square root over xi square plus delta square. Let's differentiate nk with respect to temperature. So this is then minus 1 over e to the power ek over temperature plus 1 square. I differentiate the denominator. Then it is e to the power ek over temperature. And then I open the bracket. Now I need to differentiate the argument with respect to temperature. So this is minus ek over temperature square plus 1 over temperature d square root over xi square plus delta square d temperature. So here, since the energy comes into the distribution function, I do differentiate this because delta depends on temperature. Let me massage this term such a way that I will write it as a d over d delta square times Okay, let's keep it like that. For the moment, I don't need to do anything. Okay, let's now consider 2 cases. First, temperature is much smaller than delta. I have 2 terms. I have term number 1, and term number 2. Anyway, so this is 1/2 square root of xi square plus delta square times d delta square over d temperature. So in this situation, CV is 2 times sum, and I put prime because I will be summing over states in the vicinity of Fermi surface. Sum over k. So minus and minus gives me plus. So the first term is xi k square plus delta square divided by temperature square, and with a sign plus, and then minus, then this cancels out 1/2 temperature, and then d delta square over d temperature times e to the power ek over temperature, e to the power ek over temperature plus 1 square. So let's first analyze this term, and let's look at this one. Since the temperature is much lower than the Fermi energy, so the delta, this factor ek over temperature, ek over temperature plus 1 square is approximately equal to e to the power minus, well, square root of xi square plus delta square over temperature. We have exponentially small number of available states because of the gap in the spectrum. And now I can expand this square root, assuming that the energies I'm going to integrate are smaller than the delta, so this is minus delta over temperature, and then times e to the power minus xi square over 2 delta temperature. So what basically I have is the integral over xi from minus omega d to omega d, and the first term is xi square plus delta square over temperature square times e to the power minus delta over temperature e to the power minus xi square over 2 delta t. And actually the second term will be even smaller, because I gave you the homework to consider what happens with the delta and at low temperatures, and you should find out, using the very same approach which I demonstrated here, that correction to the delta is proportional to something e to the power minus delta node over temperature. So this correction is itself exponentially small, so the exponent which I'm going to get is at least twice as bigger. So what remains is Gaussian integral. One Gaussian integral comes with a constant, and I only have exponent outside. And another Gaussian integral is xi square times this. So clearly the integral with delta is larger, so what I have in total delta over t, there is a prefactor square coming from Gaussian integral, which is delta times t to the power 1/2 and e to the power minus delta over t. So what I have for specific heat is that at low temperatures because of the gap, specific heat is exponentially small. So the specific heat is proportional to some prefactor which depends on temperature, but who cares about prefactor if there is a huge exponent e to the power minus delta over temperature. So CV, function of T, and this is for temperatures much smaller than that. This is actually a generic situation. If we have this gap appearing due to something else, we will have precisely the same situation. If we have bosons with the gaps, we discussed protons a little bit, and probably you have some problem with the homework, I don't remember. With the bosons, the difference is that the distribution function has minus, but again, this minus doesn't matter if the situation is gapped at very low temperature. It leads to sort of Boltzmann distribution, and all calculations should be repeated in the very same way. So for bosons characterized by gapped spectrum, you have precisely the same exponential behavior of specific heat. So, as I said, this is very, very generic property, and this is why I'm discussing it with you. So now, let's discuss the second case, namely what happens if temperature approaches to the critical one. And I gave you another problem to compute at home, namely to identify what is the behavior of the gap, because we will need it here. Because of this factor. So let me recapitulate this behavior. So we have a gap equation which is 1 is equal to G integral from 0 to d by frequency, and I have tangent hyperbolicus square root of xi square plus delta square over twice temperature divided by square root over xi square plus delta square dxi. This was gap equation where dimensions constant G is modulus of interaction times the density of states divided by 2. Okay, we said that Tc is defined from condition that 1 is equal to G integral from 1 over omega d dxi tangent hyperbolicus xi over to temperature divided by xi. So we put gap delta equal to 0, and this is Tc. And in turn, this was this log over 2 gamma omega d divided by pi Tc. This is how we found the Tc. Let's now look at this equation if t is approaching to Tc. What I do, I will Taylor expand this integral in terms of delta. So this is then G integral from 0 to omega d dxi, the value of integral at delta equal to 0, tangent hyperbolicus xi over 2 temperature divided by xi. But please see that this is temperature, not Tc. Tc is on the right hand side. Plus, I'm expanding, so let me say this is delta square, d over d delta square of this integral, which is integral over G integral 0 omega d, tangent hyperbolicus xi square plus delta square over 2 temperature divided by xi square plus delta square to the power 1/2 dxi, and I need to put it at again delta equal to 0. So without losing generality, I can say that this is some number actually which is coming with sign minus. You can see minus A times delta square. So what I have on the left hand side is 1, which is log G log 2 gamma omega d over pi Tc. This is 1. This is what is on the left hand side, is equal to G logarithm 2 gamma omega d over pi T, because I have running temperature here, minus G A delta square. So I combine terms, and what I have in the left hand side is logarithm T over Tc is equal to minus A delta square. So I add Tc and subtract Tc. So what I have is logarithm of 1 plus, actually minus, Tc minus T over Tc is equal to A delta square. Now, if temperature is approaching Tc, this is my parameter modulus tau. I expand the logarithm, logarithm of 1 minus x is equal to minus x, and as a result I will get square root over Tc minus T. Right? If I do calculations more accurately, I will get that delta at T approaching Tc is 3.6 square root over Tc minus T. My calculations were just estimation without carefully computing coefficient A. In principle, you do it much more accurate. Please look in the book. You use Bessel functions and take these sums and integrals in controllable way. This is what you will get. Okay? By the way, to identify behavior delta at temperature approaching, well, 0, you don't do Taylor expansion, but you replace tangent with 1 minus n. So this is 1 minus 2n psi, and you expand your distribution function, assuming that this is exponential small. This is how you get behavior gap. Okay, so now we again have two terms. We have two terms. So temperature goes to Tc. This is 2 Cv is equal to 2 times sum over K. We have the very same psi square plus delta square over temperature square e to the power minus Ek over temperature e to the power plus over temperature plus 1 square. This is the first term. And then we have minus 1 over temperature sum over K, and it's 1/2. I have d delta square over d temperature times the same factor e to the power Ek over temperature, e to the power Ek over temperature plus 1 square. So if I put delta equal to 0 in the first term, what I have is the integral over d psi, nu psi, psi square over temperature square, and some function over psi over temperature. Right? So I make it dimensionless. I divide by temperature and multiply by temperature, and I will get a contribution to specific heat of the normal metal, which is linear in temperature. This is what you compute with Jean Paul. So this is super specific heat of normal metal. And now let's look at this behavior. You see that derivative with respect to temperature of the delta square is actually negative, right? Which means that this term is positive. Therefore, if I plot specific heat now, this is Tc. What I see that when I approach to Tc from the left-hand side, from the side of a superconductor, I have Cn plus, say, delta C associated with superconductors, and this would be just Cn. So I have a jump. And d delta square over dt at Tc is just a number times Tc. So what we got jump in a specific heat, which is characteristic for the second order phase transition. So this delta Cs is just coefficient, some coefficient b times Tc, and I can write down that Cs minus Cn over Cn, this is the value of jump, is equal to 1.42. So the relative jump is just a number, and again this is characteristic for the second order phase transition. Again, what we have seen, that specific heat is in fact behaves as it's supposed to behave in accordance with second phase transition theory. Actually, with Professor Nersessian, I think you computed this jump in terms of Landau theory and expressed it in terms of parameters b and alpha, proportionality coefficient in front of tau. So basically, the specific heat experiment allows you to identify the one equation for phenomenological parameters A and B, because it will enter actually into the values of the jump, the difference. And magnetic experiment allows you to fix these coefficients in the second equation. So the penetration depth and specific heat, which can be computed from microscopic theory, this is what we did. There is no phenomenology here. And the same thing computed with the phenomenological Ginzburg-Landau theory, established connection between phenomenological coefficient A and B of Ginzburg-Landau theory and macroscopic and the coefficients related to property of the metal, such as density of states at a Fermi level, critical temperature, and so on and so forth, which is related to Debye frequency. And thus we can justify that the Ginzburg-Landau theory, first of all, can be derived from microscopic theory. It has been done almost immediately after BCS. And second, we have a connection between phenomenological coefficients and microscopic parameters of the theory. Okay, this is what I wanted to show you on the blackboard. Now I switch the gear and we will see a summary for the superconductivity. Any questions? Again, due to lack of time, I'm not able to give you more information about superconductivity. What is beyond scope of this lecture is Josephson effect, which is very important. Discussion of superconducting films. So what happens if you have quasi two-dimensional geometry? Microscopics theory. I think it goes on.